Hi, we are continuing our discussion of the memory hierarchy, and this lecture we will discuss the virtual memory. And the concept of the virtual memory, let's go to the whiteboard for a sec here. And basically, we have the CPU, um, obviously, uh, presents the request to the cache, and you can have one level and multiple levels. We'll assume you have one level. And then you have here the main memory where the cache interacts with the main memory here. Okay. All right. So what we said that the cache is a copy of the main memory. And let me just if let me just make the main memory a little larger here. Okay. So this is the main memory. Okay. So the cache is a copy or a subset of the main memory. And I have to be careful of a copy or a subset because in some policies like the write back, the cache is updated with the fresh data compare to the memory, but it has a subset of the data. And then the main memory will have a subset of the data from the virtual memory or the hard drive. Now, uh, why we needed the hard drive, and let's talk about this for a sec. In the old days of computer system, people were limited in with the memory, with the physical memory, whatever they have implemented in the motherboard. So if you have, let's say, 16 megabyte, you are limited with the addresses of 16 megabyte. People found out that this is very strong constraint, in particular when we are writing the program. So you will see that the addresses coming from the CPUs are somehow a function of the size of the physical memory. So what people wanted to do is to decouple the size of the physical memory, which is the main memory, and the addresses that we are writing to. We would like the programmer to think of a virtual memory, which is if we, for example, have an address of 32-bit address, we would like the programmer thinks that we have 2 to the 32 bytes in this virtual memory. Okay, but what physically we could be implementing much less than that on the physical memory. Oh, so always the programmer thinks of the virtual memory and write addresses for that virtual memory. And in the physical memory, we will have somehow to work our way to copy certain section to the physical memory from the virtual memory, exactly the way we have done by copying certain blocks from the main memory to the cache. But now the problem becomes larger inside. Instead of copying a block from main memory to cache, now we are talking about a page, and the page is much larger. So we tell the programmer, write the addresses as if there is a virtual memory which can sustain this 32-bit address in the case of MIPS processor, and has 2 to the 32 bytes, but with the physical memory that is implemented, main memory in your memory, it will be smaller than that. Do not worry, we will have the main memory and the hard disk to interact in a very similar fashion, the way the cache and the memory interacted. In other words, the main memory will be a subset of the hard disk. Okay, so this is the idea of the virtual memory. Also, the virtual in the older computers, it was one single user that can use the computer system. So to facilitate multi-programming, multi-users, you needed to have some kind of this setup of the virtual memory, and you organize the protection schemes via the page table, which we will talk about very shortly. Okay, with this introduction in hand, let's go to our lecture. Okay, So basically, the virtual memory here, the main memory becomes like a cache for the secondary storage, which is the hard drive here, and it will be managed by somewhat the hardware and the software, and obviously the hardware is represented by the CPU, and the software here is the OS. Now, we will have to support the sharing of the main memory by multiple programs, and once you have multiple programs and multiple, so now we talk about private. We need to get private virtual address space and apply some kind of protection schemes. Okay, so that is all with the same package of allowing virtual memory. Now, as we have said, that the data copied between the memory and the virtual memory now we'll call it a page, and the page typically is much larger than the block. The block, which is between the cache and the memory, is somewhat in the k bytes. So you can increase that by 4k bytes, etc. But in terms of the page, so the page is really in a neighborhood of 64k byte, so much larger than and probably much larger than the block, which is between the cache and the memory. So we'll call it the page. The miss here, we will give it a name of page fault. Whenever we do not, when a page does not exist in the main memory, we will call this a page fault. Okay. And now, so there is this concept now where we really have this address, virtual addresses that are coming from the CPU, from the programmer, as he or she writes their program, and this is a virtual address. And here we need to translate it to physical address, because this is where my main memory is accessed by a physical address. Okay, main memory. So somehow we need to do what? Address translation. So this address translation translates a virtual address to physical address. That's the meaning of address translation. Now, when we do have an address translation, sometimes we will find this. So this is my main memory now, my main memory. Sometimes I find the page, and that would be good. And sometimes the page is not in the main memory, and this is when a page fault occurs. Okay, so in other words, if you look at the virtual address here for MIPS processor, it is a 32-bit. Okay, 32-bit. This address, it has two subsections. One is called page offset. Okay, that reminds me with a block offset. Yes, that's for the cache interaction with the memory. So that block and was very small, but here the page offset is larger in terms of number of bits because the page is large. And then I have page virtual page number. That virtual page number will go into a translation process, basically a table we'll see shortly, and it will translate the virtual page number into physical page number, and I will drop the page offset as is, and now I have my physical address. This physical address is what the memory my main memory recognizes. The main memory is accessed by the physical address, not by the virtual address. Okay. All right. So this is so it says here page sizes 4K. I believe page sizes will be typically nowadays are larger than that. Okay. So um, now, so what happened when page fault occurs? Well, there will be a penalty, much like we had miss penalty for the case. Oops, for the case for so we had miss penalty. Okay, and we identify this as the number of cycles I need to copy a block from main memory to the cache. Okay, so now I have page fault penalty, and this page fault, I will have to pay it whenever there is a page fault. In other words, I'm trying to access a page, right, in the main memory. So this is my main memory, and there is a page here. I'm trying to access this page but oops, it's not. This page that I want is not in the main memory. So this is my main memory. So in this case, what do I have to do? I'll have to fetch this page from the hard disk or the hard drive, and bring it all over to the main memory. So the page must be fetched from the disk. This typically takes milliseconds. Of course, you don't want to wait for this. So typically, this is handled by an interrupt inside the OS, and obviously you want to minimize the fault rate, the miss rate for this to occur. So what do you have? Well, this main memory has to be fully associative to minimize the miss rate as much as possible. And obviously you have to have a smart replacement algorithm, much like the least recently used algorithm. Okay, now page tables. So obviously we need a page table, and what is a page table? We discussed a few seconds ago that there is this translation process, a translation when we translate the virtual page number into physical page number, and notice the offset is not changed, and the physical page number and the page offset, both of them create for me the physical address which I can access the main memory for with it. Now we said that when we change or when we translate the virtual page number to physical, how do I do this? Well, there is a table, and oops, there is a table. This is the table right here. This is typically, this table is called page table. It is saved in the main memory. This table is really a huge table, and it is the start address of it. It is typically pointed to it by a register. We call this page table register, and we index it, we offset it by the virtual page number. So therefore, the height of this page table equals the number. Oops, let's see, equals so, equal number of virtual page virtual page virtual pages. Okay, so how many virtual, you have a million virtual pages, that's the height of this table. So what's inside this table, in other words, what is the width of this table? I would like to call every one of those page table entry. The width of the page table entry, at a minimum, I need to get the physical page number, which is right here. So that has to be part of this entry. Then you have status bits like valid, like the valid bit, and other status bit for the OS for protections, etc. Okay, so that's the width of this page table entry. So again, this page table provide the translation from the virtual page number to the physical page number, so that I can produce the physical address. And the pointer to this page in the main memory is saved in a page table register inside the CPU. Okay, that's good. What else I have? So the size of the physical memory. Now this is my physical memory. Now consists of, let's say, pages. These are pages. Okay, so these are pages. This is a page, this is a page, this is a page, etc., etc. The size of my physical memory is how many physical pages I have times the page size. So in this example, for example, I have 4 pages times, let's say every page is 64K byte. That's the size of my physical memory. Now, what's the size, the physical, the number of physical pages? Well, which means those. I can tell this by counting, or by taking 2 to the power how many number of bits are there. Okay, so suppose in the physical page number I have 2 bits, then how many physical pages I have? 2 to the 2. Suppose the physical page number is 3 bits. How many physical pages? 2 to the 3. Okay. And what's the page table size? Well, as we explained, it is number of virtual pages times, this is the height, times the entry size. This is the width. That's the size of the physical pages. So for example, before getting to this example, so let's go over this slide very quickly. So the page table basically stores the information for the translation. It's an array, okay, and pointed to it by the page table register, which is in the CPU. If the page is present, that means a valid bit is one in the memory. Then the page table entry stores the physical. Okay, so the valid bit indicates if the page in the physical memory or it is not. Now, if the page is not, then the page table entry can refer me to a location in the swap space or in the which is in the disk or on the hard drive. So the valid bit importance, it tells me whether the page is in the main memory or is in the it's not in the main memory, it's in the hard drive. So um, let's take an example here, and this example basically show me that I have a page size of 4 addressable units. Okay, so this is a page here, 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 okay, and this is a page here, etc. And obviously, I can see here I have 32 pages in my virtual memory. This is, of course, is a simple example, and 4 pages in my physical memory. So my physical memory is smaller than my virtual memory. So here, the my physical pages equal 4 pages. I can see them, right? 4 pages. And the physical memory size, what's the size of the physical memory? Number of pages times the page size. That's 16 addressable units, bytes or words, whatever you want. What's the size of the page table? How many virtual pages I have? 32. What's the size of everyone? Status bit plus 2. Why 2? Well, because the number of physical pages I have are 4, and I can express those 4 by 2 bits, right? This is 0 0 0 1 1 0 1 1. So I need two bits for that, plus the status bits for the OS. That's the size of the page table. Okay. And now we can see that uh, using our virtual page number, we go to this page table, we see which page is in the physical memory. You can see here, for instance, whenever I have the page in the physical memory, the valid bit is 1. Whenever I have the valid bit is 0, you can see the page is in the hard disk. Okay, secondary disk storage. So that's basically the process of translation that occurs in the page table. Okay, so the page table basically map page to the physical memory or to the disk storage. Of course, if it maps you to the disk storage, it means that we have a page fault. The page that I'm looking after is not in the physical memory. Okay. Now, to reduce page fault, in other words, miss rate, we prefer least recently used replacement, which means if in the main memory, so this is the main memory. So if I need to remove a page, suppose I have a main memory of 4 pages. Let's say, well, this is what 2 and 3, and all of them are used. Okay, all of them are used. Okay, and now I need to what? I need to replace. I need to remove a page so that I create a space for a page and then bring the page that I want from the hard disk. The question is how to replace, which page of those I need to replace it? Well, we need to use least recently used. So this page has to be least recently used. For example, if the axis is as such, let's see, take another pen here. This page is accessed at 9 o'clock. This page is accessed at 8 o'clock, at 10, at 11. Then this page is least recently used. So I remove it from the main memory, and send it to the hard disk if it is dirty, or copy on top of it right away if it is not dirty. So now, how of course, when you have millions and millions of pages, then really this applying this least recently used as is becomes very difficult. So what we do, we use something called reference bit. Oh, okay, so we're adding another bit. Remember the valid bit, which indicates if the page is in the if the page is in the physical memory or the hard. So we're adding another bit, which is the reference bit. So this is adding another bit, which is the reference bit. Okay, so let's see what's the reference bit. The reference bit, what happens is periodically the OS goes and clears all the reference bits for the pages in the memory. Then if page is accessed, all right, we will set this reference bit to 1. And now, once we need to replace a page, we search for these pages with reference bit equals 0, which means those pages have not been referenced since the last periodic clearing. So that's one way to approach it. Okay, and now the question is, since the disk writes take millions of cycles, we cannot really apply this write through policy, which means when we write to the main memory, we must write to the hard disk. That is impossible to do because, well, it is close to impossible, practically not possible, because the hard disk is very, very slow. Then what we do, we use a write back policy, which means I keep writing to the main memory, and when I flush a page out I replace a page, I check if this page has been modified by the dirty bit, yet another bit. You see a reference bit, dirty bit. The dirty bit is a bit which indicates that this page has been modified since it was brought from the hard disk. If it is modified, it means when I replace it, I need to copy this page to the hard disk. So this is you for the write back policy, which is the only practical policy. So we write to the pages on the main memory, and then when we replace the page, we check if the dirty page is set. It means that this page has been written into, and it has to be copied to the hard drive before I bring the new page in its place. Now, what happened is that let's see if we have, if we go to just to quickly to the whiteboard here, and see if get a new. What happened when the CPU sends an address to the cache, and here the cache sends the address to main memory. Okay, so let's say we are missing on the cache and we send this address to main memory. We are reading from main memory here. Okay, and what happened is that we realized that uh, every address we produce by the CPU, it has to be translated from virtual addressing to physical addressing, and that we need the page table for. And funny enough, this page table is in the memory. So to do this translation from virtual to physical, I need to access the memory to do this translation so that I can access the memory. So in other words, I need to access the memory twice, one for the page table and the other one to access my word, whether it's in the cache or in the main memory. So becomes really cumbersome. Somehow this translation has to be quick, and I have to move it to inside the CPU. I should not be wasting one cycle to translate from one cycle, well, I'm sorry, one access. I shouldn't be wasting one access to memory to translate from virtual address to physical memory. And I have to move this to the CPU, and this is the job of a hardware called translation look ahead, translation look aside buffer, TLB. Okay, so let's go and see what's the job of this TLB. Okay, so the address translation would appear to require extra memory reference, one to access the page table entry and then access the memory. So I'm having two access memory accesses. But to access we know that this page table has really excellent locality. So what I could do, I can group few of those entries that I'm using from the page table and put it in a small cache. I'm gonna call that cache look aside, translation look aside buffer. Typically small, okay, and has a very quick access time, and really it has very low miss rate because we hit the pages many times before we move to other pages. Okay, so this is the job of the TLB. So you can see that the TLB does a quick. If I may, I want to just make sure that we understand where the boundaries are. This is within the CPU happening. So I have the virtual address. Okay, here is the virtual address, and from it I get the virtual page number. I access the TLB, which is a quick cache. Now, if I find my which I hope, if I find my entry in the TLB, then I will do the translation very quickly. I will get the physical page number, form the physical address, and then I can access the memory. Okay, so but if I don't find it, unfortunately, then I will have so this is a page hit. This is a page hit, and if I don't find it, I will have a TLB miss. And in this case, TLB miss, what I will need to do is that I need to bring the entry from the page table to the TLB, because the entry is for sure in the page table in the memory, and I don't have it. Okay, so if we have if we miss on the TLB, meaning I don't see the entry, uh, we have one of the two cases. Case either this or this. Let's talk about the case number one. So I have a TLB miss. Either the page is in the memory, and in this case, if the page is in the memory, the entry, I will load this page table, load the page table entry from the memory to the TLB. Now, this process can be handled either by hardware or software by the OS. Okay, if the page is not in the memory, meaning I have a page fault. Okay, so the TLB miss can lead to a page fault, but the TLB, so the TLB, we talked about two cases: page in memory, in physical memory, and page is not in physical memory, and this is where page fault is. Okay, all right, so in this case, the OS will handle the fetching of the page from the hard drive to the main memory, and then we restart the faulting instruction. Okay, and for that we really need handlers, and these are specialized routines in the OS. So they handle the TLB miss handler. Uh, it should tell that if the page is present, in the physical memory, but it's not in the TLB, and in this case, or the page is not present, because these are the two cases that we discussed in the earlier slide. Okay, we must recognize that the TLB miss before doing any writing of registers, and and the handler obviously copies, in the case of the page table entry from the memory to TLB, in the case where the page is in the physical memory. And we can restart the instruction. Okay, if page is not in the memory, then a page fault occur. Okay, what happens in a page fault? Okay, another specialized routine. So because if the page is not in the physical memory, we delegate the task to page fault handler. And in this case, the page fault handler, what it does, it try to find the entry, page table entry, and try to find the page on the disk, because the page is not in the physical memory. That's why we are having a page fault. We choose the page to replace, and obviously this is in the main memory. So now we go to the main memory. We'll say, okay, we need to choose this page. This has to go out. Now, well, do I need to copy this page to the hard disk? We check. If the dirty bit is set, it means we have written to this page. It means we have modified this page. Then yes, we need to copy this page to the hard disk. If it is not, then we don't need to copy it. We bring the other page from the hard disk on top of it, because we don't need to copy, because this page is the same copy as the hard disk. Now we read the page in the memory, and update the page table, and then we make the process runnable again. We will hit TLB miss, then we will move the page table entry to the TLB, and execute the instruction again. Now, the question is, the the cache, um, does the cache system use the physical address, or the virtual address? So this is the cache subsystem. So this is the cache subsystem here. Okay, this is the cache. You can see we're getting cache index, tag, block offset, byte offset, all that. This is the cache subsystem here. What does it do? Preferably, the cache is better to use physical address. So what we do, we do the translation. You can see here's the TLB. We do the translation from the virtual address to the physical address, then we access the cache subsystem. And we take the physical address, we partition it, we say, well, this is the tag, this is the index, and let's take the index, access the set, do the comparison for the tags, determine hit, miss, etc. No, you could use the virtual address, not recommended though, because multiple virtual address can map to the same physical address. So we would want to have really, with the cache subsystem, deal with the physical address. Okay. Now we have different, since we allow multiple programs to run, we have to implement some memory protection scheme. Obviously, the hardware must provide a mechanism for the software or the OS. We should have privileged supervisor mode. We should have privileged instruction. We should have the table, the page table, and the state information inside that page accessible to a supervisor mode, so it will allow certain, it will set and reset certain bits in that table. Okay, with this, I conclude the section, okay, and of the virtual memory, and we'll continue the discussion in the next part.